I saw this meme on LinkedIn the other day. And this is me, by the way, because some of you guys think that I'm an AI slob. This meme is funny that is showing most people learning simulation immediately jump straight to the last step, which is opening the software and using the specific physics. Because they love the colors and the animations, but what they don't realize is that underneath all of that, it's math, it's physics, it's numerical methods. And I've been there too. And over the last 5 years of learning simulation, I've made a lot of mistakes. So here are the 5 mistakes I wish I had avoided when I started learning the finite element analysis. Number 1 is starting with the software. This was probably my first mistake. You open the simulation software and then you see these beautiful simulations and you see the colors and everything and you get amazed. I remember making a simple cantilever beam simulation. I also calculated the problem analytically and then I compared my analytical results with the finite element. And they didn't match. And I remember thinking, wait, is the simulation wrong? I went to my professor and asked him about it, and basically the answer was, it's finite element. You need to understand what finite element analysis actually is. That was an important lesson, because I was treating the software like a calculator. I give it geometry and material properties and boundary conditions, and I press run, and I expect the exact answer to appear. But that's not what the finite element analysis is. Finite element analysis is a numerical modeling method. You're taking a physical problem, representing it mathematically, making approximations, discretizing, and then solving the result computationally. It is basically a matrix. It is math. So before spending months learning where every button is, understand what is happening behind the button. And don't limit yourself to finite element either. There are many other ways to build computational models. You have the finite difference, finite volume, agent-based modeling, analytical methods, and even approaches that combine different methods. I made another video about other computational modeling methods other than the finite element, so I'll link it here and I'll leave it below if you want to explore them. Problem number 2 is jumping straight into 3D. The second mistake is something I see all the time. It's real objects, so I need to simulate the entire 3D object. Not necessarily. Before opening the software, ask, what question am I actually trying to answer? Let's say that you have a wrench, and you want to know what's happening around a particular region where the stress is concentrated. Do you really need to model the entire wrench in full 3D? Maybe and maybe not. If the geometry and loading allow it, you might simplify the problem. Maybe the thickness is small enough that a 2D approximation is reasonable. Maybe the geometry has symmetry, so you only use half of it. And sometimes you can reduce the problem even further. You can have 0D, 1D, 2D, and 3D, depending on what you're actually trying to calculate and the level of complexity you want your answer to handle. So instead of asking, how do I simulate this entire object, ask, what specific equation am I trying to answer? Then choose the model that can answer it. Mistake number 3 is not understanding the mathematics underneath. So imagine you have a heat transfer problem. You want to see the heat distribution over a specific object. Before doing the simulation, ask, what equation is actually describing this problem? And if you understand the mathematical structure of that equation, the general solutions, you can start asking much better questions. Do I even need a numerical method here, for example? Because sometimes you don't. Maybe the geometry and all the conditions is simple enough that you can derive an analytical solution for it, a simple mathematical expression. And if an analytical solution is available, that's incredibly useful. You can use it to understand the problem, and you can use it to validate your numerical methods. And regarding the heat equation, I have demonstrated the general solution for the heat equation in another video. I will link it here. So I think one of the most useful things you can learn is to recognize, what mathematical problem am I actually solving? And a lot of physical problems can eventually be expressed as differential equations, often partial differential equations. And numerical methods such as FEM are ways of approximating solutions to those problems when the exact analytical solution is difficult or impossible to obtain for the problem you're interested in. This is one reason I spend so much time studying mathematics. 2 resources that helped me a lot here are Advanced Engineering Mathematics by Schrod and Partial Differential Equation for Scientists and Engineers for Stan Lee. Mistake number 4 is thinking a finer mesh always means a better answer. Now we get into one of the famous rules in simulation. Make the mesh finer. Your results look strange? Make the mesh finer. Your stress doesn't match. Make the mesh finer. You don't trust the answer? Guess what? Make the mesh finer. But does finer always means better? Not necessarily. The question is whether your result is converging. For example, imagine we calculate a stress value. With mesh 1 is 142 megapascals, with mesh 2 is 157, mesh 3 is 161, mesh 4 is 160. Now we're starting to see the results stabilize. This is called the mesh convergence, where you settle on one mesh that is showing a consistent results and you just settle on that. And there is another problem. You don't just want to blindly refine everything. Imagine you have a sharp corner or a region with a very large gradient. You refine the mesh there and suddenly you create very different element sizes next to each other. The solution can change dramatically in that region. And in some problems, the quantity you are looking at may not converge to a nice finite value at all. So you need to understand, why are you refining the mesh? Where are you refining it, and what quantity you're checking for convergence? Don't just press automatically generate mesh and assume the computer have made the numerical decision for you. The mesh is part of the model, you need to understand it. Problem number 5 is ignoring the solver. So now we know that the finite element model is kind of a big matrix. The computer has to solve that huge system, and that's the job of the solver. So for example, you might have direct solvers or iterative approaches. In multiphysics and CFD software, you can also encounter segregate approaches, where different groups of variables are solved sequentially rather than all at once. It may be useful to understand the basic ways we use to solve a matrix, like the Gaussian method or the LU decomposition. And you can find this stuff at the previous references I mentioned before. So the choice of the solver have a huge effect on computational time and robustness, or accuracy. And sometimes the accuracy of the results are being compensated for time, so you need to understand that. The solver is part of the numerical method. You should understand it at least at a basic level. Don't just treat it like a black box. So, those are the 5 mistakes. To summarize, number 1 is starting with the software. Number 2 is jumping straight into 3D. Number 3 is ignoring the mathematics. Number 4 is assuming a finer mesh automatically means a better answer. And number 5, treating a solver like a black box. And if I had to summarize all 5, it's actually one mistake: not understanding the problem before trying to solve it. Before you open the software, ask, what is the physics? What is the mathematical problem? What assumptions can I make? What is the simplest model that can answer my question? How am I going to solve it? And finally, how will I know that the answer is correct? Because simulation isn't just about producing a beautiful result, it's about understanding why you should trust it. And that's something I've been learning for the last 5 years. If you want to learn more about computational modeling, finite element, and other methods engineers and scientists use to simulate the real world, you can follow the channel. Thanks for watching.